My name is Wendy, and I'm going to be talking with y'all tonight about Nami, a serverless framework for consuming webhooks at scale. And I worked on this project with a couple of other developers. It is built using Node.js and the AWS SDK for JavaScript. It's a command line interface tool that deploys a primarily serverless architecture for handling large influxes of webhook traffic. It's also published as an NPM package, and it is open source. All right, so this is just a little preview of the deployment sequence. So we've got each piece being deployed to the cloud, and then our endpoint is output here to be registered with a webhook producer. So any AWS users here? Lots? Okay, all right, not everybody. Well, you probably have a sense then that there's a learning curve and some hidden complexities there with using AWS, right? Even a seemingly simple, discrete task can actually be composed of multiple micro tasks under the hood, right? And that complexity does grow when you're deploying multiple services and trying to get them to talk to each other nicely. So that's the complexity that Nami does try to abstract away from the developer. All right, so here's an overview of what we'll be talking about tonight. So I'm going to do a brief review of webhooks and event-driven architecture, and talk about Nami and the problems that it solves. I'm going to walk you through some of the design decisions that we made when developing the framework. And then I'm going to talk about some challenges that we encountered along the way, some optimizations that we were able to make in response to those. And we'll touch on future work. Okay, so here's an example of subscribing to a webhook. This is with GitHub. And you can see in the payload URL input, we've got a Nami generated endpoint. And then you can select the content type that you would like for your payload. In this example, it's JSON. Then you would select the event or the events that you would like to trigger a request to this URL. And this is just GitHub. So with GitHub, one of those events, for example, that you might subscribe to is a push event, but you can select individually. All right, so webhooks are really just about moving data from one place to another, from point A to point B, right? And so that sounds like APIs, right? But a big difference there is who's driving. And so APIs are really seated in this request-driven paradigm where a client initiates a request to the server and expects some data in return, and that process is synchronous. But the client can't predict when that data is going to be available. It can't predict when the event is going to occur on the server. So it has to continuously send these requests, just hoping that it's going to get some data back. And as you can see, this is a pretty inefficient way to transmit data, because it's only after an event actually occurs that there's going to be data to return. So this creates an unnecessary load on both systems, the client system because it has to continuously send these requests, and the server because it has to continuously respond to them, and most of the time it doesn't have anything to send back. So that's going to be, that problem is going to be especially pronounced when data is only rarely available. Webhooks, however, turn that situation around into a don't call us, we'll call you scenario. So instead of the consumer initiating the request, with webhooks, the request is coming from the event producer. It's only occurring in response to an event. And you'll notice we're no longer talking about client and server here, but event producer and event consumer. So much more efficient way to transmit data. With webhooks, the producer doesn't actually need a response from the consumer to continue with some task. So with APIs, we're in this request-driven architecture. So primary characteristics of that were synchronous. So when the client sends the request to the server, it does need that information to continue on with some process. It's also request-driven, so the client does have to initiate the request. And then here, the response is meaningful. So the client does need the information that's contained in the response. But with webhooks, we're moving away from this synchronous request-driven architecture toward an event-driven one, where we're just sending requests in response to events that have happened. So there's a few important characteristics here for an event-driven architecture. One, it's asynchronous in that the client is no longer waiting for server to send back some information. The server, the event producer is actually just pushing data to the consumer in response to an event, and it doesn't need a response to continue with its execution. Also, it's driven by the event rather than a request from a client. So that request only happening when the event occurs. Also, the response here is acknowledgement only. So it doesn't really have any meaning here. And it's actually only here because we're working within the limitations of the HTTP protocol. But that asynchronicity that event-driven affords us and the event-driven updates do come at a cost. And mainly that's that the consumer of the event can't control the flow of data. So events just happen when they happen. So when events occur in batches, then that can generate thousands of requests instantly. And it's that kind of traffic pattern that does threaten to overwhelm webhook consumers. So a couple of examples. So we did some reading and found some engineering teams that wrote about experiencing exactly this type of problem. So Jira, project management issue tracking software, their system generates webhooks in response to when issues are modified or added or deleted. So they were seeing this problem when customers were updating issues in bulk. And at that point, they were receiving a huge traffic spike because a webhook was being generated for every single issue. Next, we have Rewind, which is a real-time backup service for Shopify. So you can think of it as like Apple's time machine, but for Shopify customers. And so they were experiencing this type of traffic when Shopify customers would do things like import entirely new inventories and say that inventory had 10,000 items. And Rewind is subscribed to that webhook that tells them when an inventory item is created. So for every single item on that inventory, so you've got 10,000 webhooks, massive traffic spike. Okay, so that's our first problem, is that bursty, inconsistent webhook traffic. And so as we talked about with those examples, that can happen with bulk updating or events occurring in batches. And the problem is that you can't control the flow of that data. So the consumer can't just tell the producer to slow down when it's being overwhelmed. So what does this kind of traffic look like on your infrastructure? Okay, so with always on servers, you are just happily handling your request for some time until you experience that big wave of webhook traffic. But there's no means for you to scale those servers instantly, and so the infrastructure just can't handle the load. So what's the off-the-shelf solution for that? More servers, right? So you purchase hardware, you extend your backend code, deploy the infrastructure, and you're good to go, assuming that you've predicted the worst case scenario. But the problem here is between the squiggly line and the dotted line. All that white space, or most of it, is idling resources. So they're sitting there waiting to handle those big bursts of traffic, but most of the time they're doing nothing. So the question is, can we dynamically adjust based on incoming requests? And the maybe not so surprising answer to that is that yes, we can, using Lambda functions. So Lambda is AWS Functions as a Service offering. There are other FaaS vendors, Google Cloud, Microsoft Azure, and others, but here we're just talking about AWS Lambda. So with FaaS, your code is run in compute containers, but the provisioning and management of that server power is abstracted completely away by the FaaS platform. So all you need to do is upload your code to the platform, and then the provisioning and management is completely handled for you, and scaling is automatic and elastic. So you're only paying for the amount of time that these functions are spending in execution, and you're not paying for any idling resources. So Lambda functions are great helpers because they show up when they're needed, as many as you need. They do the work you need them to do, and they leave as soon as they're done, and so you're only paying them for that precise amount of time that they're working. But let's zoom out for just a second and look at serverless. So here we have a continuum of infrastructure management. And to the far left extreme, there's where your bare metal on-premise servers are. So if we hop onto the continuum, just to the right of that, we've got infrastructure as a service. So infrastructure as a service does virtualize those bare metal machines, but you're still managing operating system, networking, security, etc. On the other end of the spectrum, we have serverless. This is where FaaS falls. And in this case, like we said, provisioning and management is all abstracted away, and scaling is automatic and elastic. If you look just to the left of that, you've got platform as a service, which is similar to functions as a service, except that scaling is not automatic and still needs to be configured. So the automatic scaling is what we want to leverage with FaaS to handle our bursty webhook traffic, right? The trade-off with all that abstraction is a loss of control. So for example, you don't have any control over or introspection into the life cycle of a Lambda compute container. So let's look at Lambda compute container. Okay, so when a Lambda function is invoked for the first time, a container is spun up, and it's provisioned with all the resources, the memory, the dependencies that are needed for your function to execute. So multiple functions can be executed sequentially in the same container. And as long as the container's been used relatively recently, it stays warm and is available to be reused by future functions. As long as the container is not currently in the middle of executing a function, then it can be reused. And that's what's happening here. So there's no scaling happening here yet. So let's look at Lambda scaling. Okay, so with our bursty traffic and a large number of events being generated over a short period of time, chances are that the rate of incoming requests is going to be greater than the time it takes for that first container to complete execution of your function. So in that case, the container is still in the middle of executing when the new invocation comes in. So to respond to that, Lambda spins up an additional container. And then if another request comes in and triggers an invocation, those two containers may still be in the middle of executing that function, so a third container is spun up. And you get the idea, that's a general pattern. So it's these multiple containers, concurrent containers, that are what allows for Lambda's concurrent execution, and that's the unit of scale for Lambda. AWS does impose a default per account limit of 1,000 concurrent executions for Lambda. So this is what that Lambda scaling looks like with our bursty traffic. So each of these circles represents a container, and you can see that they increase concurrency when requests come up, and they decrease concurrency when they go back down. Okay, so Lambda has taken care of our bursty traffic pattern, but we still need to throttle the data, process it, and then put it into some persistent store for later retrieval. So let's take a look at a system that can take the event data on its journey from coming in as a request to where it's put to rest. And Nami's solution stands up this constellation of AWS services, starting with API gateway. Then we've got a Lambda layer, we've got a queue, another Lambda layer, and then the data store. So this is the path that event data travels until it's at rest. So what does it take to actually set this up? Okay, there's a couple different ways. You can do this via the AWS Web Console, but that's certainly a lot of clicks and page load times. And if you want to handle a second subscription, you have to do that all over again. Alternatively, you can do it programmatically using the AWS SDK and make API calls. And so that's exactly what we did. We counted the number of API calls that it did take, not including helper functions, scripting, anything else, and it's over 50. So with either approach, you definitely have a complex setup process. There's a learning curve, that's setup time overhead. You have to have a considerable amount of knowledge about each service, and then it takes some digging to determine the right sequence of commands to get these services talking to each other. And that's all time spent away from your core business problem. So what we need is a framework to abstract this complexity away. And that is what Nami does. So we bundle all the functionality to do that into a single command. And so now I want to walk you through some of the design decisions that we made during development. And here's the major components of the Nami system. Not many, but there's a lot happening between them. So we're going to visit each component starting with Lambda. So this is the core piece of our architecture. It's receiving those requests It's handling them by sending them on to be stored, and then it's returning that response to the webhook producer. With this Lambda, we wanted to keep execution logic really lean so that it could provide that quick response to the producer and also to maximize scaling by minimizing the function execution duration. So all they need to do is receive the request, send the payload on to be stored, and then return that status to the producer. So now we need to store the data so that the developer can hook into it for retrieval. And we do that using MongoDB deployed with Docker on an EC2 instance. So we've chosen MongoDB NoSQL data store because a document database is a great fit for the nested JSON structure of our webhook payloads. Because we expect to be receiving webhooks coming from any producer and for any event, we expect the schema to be volatile, and so we really need the schema flexibility of that document database. Now, AWS does have a few managed service offerings for document database, but we don't use one for a few reasons. One, our use case doesn't really call for any of the features of a managed service. Two, some of the offerings that could otherwise be a good fit for us actually cost more for write-heavy usage, and we're definitely write-heavy. Also, they're less mature as services than MongoDB, which has been around over a decade. So in the absence of a compelling reason to use a managed service, we do prefer to return control back to the developer when the data is at rest. So we deploy MongoDB on an EC2 instance, which is AWS virtual machine offering. And we do that automatically by passing in a bash script to the SDK call that's used to run the instance. We do deploy the database using Docker as opposed to direct installation. And that's because the containerization that's offered with Docker allows us to decouple the application running inside of it from host system configurations. So that way we avoid potential for conflict between the install and the host system. One caveat about EC2 instances is that by default, they only have ephemeral instance storage. So if that instance were to ever temporarily stop running, then all data in memory is lost, and that's bad. So we overcome that by attaching an elastic block store volume to the instance. EBS is AWS disk storage offering for EC2. And you can see in the code snippet on the third line, hopefully you can see, where we do the volume mapping between the EBS volume and the MongoDB data directory in Docker. So we do introduce a few significant problems here. So with many thousands of requests coming in at any given second, we run the risk of overwhelming the number of available connections that the instance can handle. And so we need to slow down the flow of data so as not to overwhelm our downstream resources. And while it is possible to provision a larger instance size that can accommodate more incoming connections, we still have this problem of tight coupling. And with tight coupling, we have a potential for data loss with any downtime if the EC2 instance were to temporarily stop running. So we need to introduce some fault tolerance to our system. Also, we want to be working with the event-driven model rather than against it. So if we hold the connection open to the webhook producer while we open a connection to MongoDB, process the payload, write the document to the database, and then finally respond to the producer, then we're really undermining that concept of the asynchronous consumer, which is one of the major benefits of an event-driven architecture in the first place. So if we do this kind of synchronous processing, then the producer is subject to the consumer's processing time and failures. So what we really need is for this Lambda to just fire and forget the webhook payload, sending it on to be stored without waiting for that process to complete. And so that way it can return an immediate response to the webhook producer. So we need to just get it, store it, ack it, and that means don't do that processing while holding the connection open. The Lambda should just fire off the webhook data without having to worry about how it gets stored. It can just trust that it will be. So to address these issues, we insert a queue between the Lambda layer and the data store. The queue acts as a message broker. So it queues, routes, and delivers those messages. And it's optimized for high concurrency and throughput, so it scales well with our Lambda. The queue does several things in our architecture. It slows the flow of data by buffering messages until the consumer is able to receive them. It provides some fault tolerance for us in the case of failure. And it enables asynchronous processing by decoupling producer and consumer. And with this decoupling, we're fully embracing the asynchronous, event-driven nature of a webhook handling system. So the producer doesn't need to know what the consumer is going to do with the data, or even if it's available. And the consumer doesn't need to know anything about the producer. It can just count on messages coming out of the queue. And so when the producer and consumer are decoupled, they can be scaled separately. So the producer can be scaled way up without overwhelming the consumer. So the queue is an integral part of our system now, but the trade-off of adding it is adding additional infrastructure complexity. So that does introduce a few new problems for us. One is, how do we get the message from the queue to the data store? Then how can we perform any processing that we need on that data, such as cleaning off all that message metadata that got all over it as it was coming through the queue? And then how do we allow users to send that data on to other external systems? And the answer to that is another Lambda layer between the queue and the data store. So this Lambda can connect to MongoDB. It allows us to perform additional heavy lifting processing of those messages, and it enables us to send the data to other external systems. But we have introduced a new problem here. And that is that, recall earlier when we were talking about the awesome scaling capability of Lambda. Well, in this case, we actually don't want that, because then we've just reintroduced the problem of overwhelming downstream resources, and also we're competing for concurrency, because remember, AWS has that per account limit. So we're competing with concurrency with the webhook receiving Lambda, and we want that one to have maximum concurrency. So we overcome this by setting the maximum reserved concurrency on this Lambda to 5, and that gives it just enough concurrency to receive and process those messages at a throttled rate. We also want to be really intentional with our error handling in the message consumer. So in the event of an unprocessable message, which are sometimes really dramatically called poison messages or messages of death, or in the event of extended downtime of an EC2 instance, and we're going to have messages that just aren't able to be delivered. But we don't want to rely on default retry policy here, because SQS will just continue to retry sending that message indefinitely until the message retention period expires. We don't want that because AWS bills for each send with SQS, and the data would ultimately be lost after expiration of that retention period. So instead, we configure a dead letter queue, which is a place for those unprocessable messages to come to rest for later analysis and processing. Okay, so now we have our webhook receiving Lambda receiving messages from the queue and then storing those payloads in the database at a pace that we can keep up with. But we still need to make sure that that data is not accessible by public internet. And we can do that with a virtual private cloud. So a VPC is a virtual network that securely isolates the services that live inside of it. The EC2 instance is required by default to be in a VPC. And so we make the webhook processing Lambda part of that same VPC so that it can write to the database, but without opening up a public portal. Finally, we create an entry point into our system where the webhook data actually comes in, and that's the API gateway. So with webhook requests, they need to be sent to a publicly available URL endpoint. But the Lambda function itself doesn't provide this. So we use API gateway to publish that URL that can then be subscribed to the webhook. The endpoint is configured to invoke the Lambda when it's visited. And then the gateway can route the Lambda's 200 status response back to the webhook producer when it's successfully received. Also, if a user deploys multiple instances of Nami, so one for different webhook subscriptions, we do consolidate all of those endpoints under one host. And we do that instead of creating a new gateway for each one, so as not to strain the overall per account limit that AWS imposes for number of gateways. All right, so remember when I said we need to make over 50 API calls, not including anything else, just to stand this up? Well, now that we've walked through each of these pieces, hopefully you get a better sense of how big of a job this is to do manually. And so this is where Nami comes in. So the user can deploy with just one command and then grab that endpoint and subscribe it. So our framework was designed to support traffic spikes of roughly 5,000 requests per second. So we did some load testing to identify Nami's capacity to handle a heavy load of webhook traffic. We were able to consistently reach 4,000 requests per second with 0 errors and up to 4,800 requests per second before we started to see any errors, but even then we only saw 3. So we do support this expected range of 5,000 requests per second. Okay, so during development, we did encounter some challenges along the way, but we were able to make optimizations in response to those. So we'll walk through them one at a time. We do have the webhook processing Lambda reusing the database connections to MongoDB. So in Node.js, when a Lambda container is first spun up, the initialization code is executed. And that creates an execution context that's shared by all function executions in that container. So we declare a variable in that context and assign it to the database connection. So when functions are invoked, if that connection exists, then it's used, and otherwise it's created, and then it can be reused by all future function executions in that container. So reusing database connections does allow us to reduce our function execution time and to better manage open connections to Mongo. All right, Lambda memory optimization. So during development, we did notice some throttling happening on the webhook receiving Lambda. And we know that increasing the memory of a Lambda typically decreases function execution duration. So we increased from a default of 128 megabytes to 256 megabytes. And we did find that this gave us the best response times for our use case. But increasing above 256 megabytes really yielded diminishing returns. So this was the optimal level for us. Another question we face with running Docker on EC2 is what happens if the EC2 instance temporarily stops running? Docker containers need to be run in order to be used, and they stop when their host system stops. So to ensure that the container will always be available as long as the EC2 instance is on, we configure an automatic restart policy to always restart. Finally, we did encounter some challenges with timing when deploying or destroying services in rapid succession if those services depended on one another. And that's because AWS returns an optimistic response when an SDK function is invoked. So it can sometimes happen that a service is not actually in the expected state immediately after that successful response. So to overcome this, we implement some basic while looping that continually checks the status code on that piece until it's in the appropriate state to continue our execution. So this diagram illustrates how we handled that with the termination of an EC2 instance. We needed to make sure that the instance was completely stopped before we were able to delete the associated security. Some future work that we'd like to continue with Nami. We would like to add monitoring alerts that would alert the user if a message has entered the dead letter queue after failing to be written to the database. We would also like to add an alert if the main queue is filling up too fast, and they could manually intervene and perhaps increase concurrency on the processing Lambda. Also, we would like to improve customizability here. So while the user can currently customize any of the resources deployed with Nami via the AWS console, we'd like to add support to do that during deployment by passing in flags. And some of those details that we might want to customize are EC2 instance type, EBS volume size, memory configurations and timeout limits for Lambda, custom error handling and response codes, and custom message retention period, both for the main queue and the dead letter queue. So this is the team that worked on this. We've got Sachin in London, Nick in Los Angeles, and myself here in Austin. And here's how you can get in touch with me, and also where you can read more about Nami. And I'm just coming off of this project, so I'm open to new opportunities. And thank you for listening.